thank you everyone for joining me this evening. I'm here to give I guess the last talk of the day, and so I'm between you and dinner. I'll be as efficient as I can. I wanted to take a minute to describe a little bit what we're seeing in HPC and supercomputing, and share some vision, share some directions, and where, of course, Nvidia is investing. In the backdrop of HPC, it's always important to think about, and what motivates a lot of the industry are the grand challenges that we're all working on. Whether it be climate and HPC helping us to predict the impacts of melting ice caps, or how greenhouse gases will affect the world's extreme weather events. In renewable energy, where HPC researchers can actually simulate future wind farms to optimize clean energy production. Applying HPC to the global pandemic, and certainly this last few years where HPC has played a pivotal part in research for COVID-19. And beyond that, expanding to drug discovery as a whole, we're reaching the point where computational methods are becoming the foundation for future disease prevention and vaccines and disease treatments like the mRNA vaccines. And then finally, of course, understanding the universe. New instruments like LIGO and understanding gravitational waves, reaching farther into the universe to observe what's happening and also simulate it from first principle physics to understand the nature of what's going on in space, and astrophysics and fundamental physics. These are some of the grand challenges that motivate our work, that fund our work, that justify the creation of the world's supercomputers. As a result, we're also seeing how the modern supercomputer is changing in what it's being asked to do. And really there's 5 main things that are the workloads of the modern supercomputer today and moving forward. The first being, of course, simulation. Simulation will always be the foundation of HPC and supercomputing. And certainly it has been for the last decades and will be into the future, and we'll talk about that. The new workload of HPC plus AI, bringing AI techniques to science, is everywhere. 5 years ago, there was probably only about 100 papers published across the 5,000 papers in data science actually were deploying AI methods for scientific problems. Today, approximately 1/3 of all the papers being published in AI, machine learning, and deep learning are being applied to scientific problems. This is clearly a new workload for the modern supercomputer, and an important one at that. Going beyond just simulation and augmenting with AI is edge computing, connecting supercomputers to the new instruments of science and making them part of the scientific instrument themselves. We see as an opportunity to advance what modern experimental science looks like, one that's coupled deeply with computing infrastructure in a real-time scientific experiment. And then you combine those with the opportunities of digital twins. Digital twins, as you saw from this morning keynote, bringing together simulation, AI applied techniques, and even experimental science into a digital twin, and having a supercomputer that can be a proxy for the real world to experiment, both move forward in time and in the past, and explore different scenarios. And then the 5th workload that we're seeing emerge is quantum computing. We're still decades away from a quantum computer, at least one that's practical enough to apply to large-scale science problems. But the supercomputers of today can be a critical tool in evaluating and exploring and redefining, what does computer science mean when you're dealing with Schrodinger's equations, and being able to apply quantum computing techniques and rebuilding the foundations of mathematics, of computer science, to some of these large-scale problems. Supercomputers today can be that, can proxy and simulate the quantum computers of the future. So let's go through each of those 5 things. First, of course, is simulation. And with simulation, it's always a question of scale. And we're seeing 2 areas where this is always being challenged. One is climate science. Today's supercomputers are being built to study the convection at a global scale, to simulate the transfer of heat, the movement of heat around the globe. To do this, we need to actually model the entire Earth down to about a 1 kilometer resolution. And can be processed basically at minute kind of timescales in order to accurately simulate the global convection of the Earth. But it doesn't stop there. The Intergovernmental Panel on Climate Change issued a report. Step 1 is understanding convection at 1 kilometer. Their second projection was the need to get to 100-meter resolution. This is really necessary to predict some of the extreme weather impacts reliably. The complexity of hurricanes and other such events require a resolution that's much down at the 100-meter resolution. And of course, as we reduce the resolution or go finer, we also have to reduce the time step, which compounds the computational problem. And if we go a step further, we want to actually simulate accurately low-level cloud formation. To do the low-level cloud formation, we had to go a step further beyond just 100 meter down to a 1 meter resolution, and now potentially even sub-second timescales. That is a 100 billion x computational need to model for large-scale simulation of the Earth, and will drive a lot of the investment in large-scale supercomputing. The same can be applied at the microscale, the biological scale. Understanding the COVID spike and the global pandemic spurred, of course, a lot of research into understanding the physics, the actual quantum physics, the quantum chemistry of the COVID spike. This was a simulation done on the Perlmutter supercomputer with 4,400, I think 8,100 GPUs, where they actually did it in a software package called CP2K, which you guys are familiar with. Actually executed and simulated the entire COVID spike inside all of its water. Of course, water is a big part of the simulation. It's not operating in a vacuum. And this simulation actually exceeded 1 exaflop of scientific calculation, leveraging the mixed precision capabilities of modern GPUs in order to accurately predict the motion and behavior of the COVID spike, to come up with drugs that can intercept its motion and its activity. So the scale is happening for both of these problems at the global Earth scale, but also at the microbiology scale, driving simulation up as well as the size of our supercomputers. Of course, there's a new tool for computational science, and that's AI. Just like before in the beginnings, as Moore's law was tailing off on the blue curve, there was the introduction of leveraging accelerators, leveraging GPUs to offload the compute-rich parts of the computation. We saw a jump in continuing an exponential scale of growth of computing. As companies, integrators, and providers here you see the show floor have been investing in scale-up and scale-out technologies, we continue to make bigger supercomputers that can actually solve these problems as one. AI is offering yet another leap in technology and the scale of what we can do in modern supercomputers. A couple of examples I've highlighted here. ForecastNet was developed in collaboration with Nvidia, with LBNL, University of Michigan, Rice, Purdue, Caltech. And this was actually developing a neural network model that modeled atmospheric rivers, that could predict atmospheric rivers, being trained on actual data to understand extreme weather events across the Pacific. OrbNet was partnering with Entos to build machine learning potentials, to actually build a machine learning model that could predict and use as a proxy for interatomic potential energies. They actually got a 1,000x speed up compared to using first principle physics methods by using an AI approximator that learned from the real physics. SGTC, which was done for Fusion Code, working with Bill Tang at Princeton, and Argonne National Labs successfully built an AI surrogate model for modeling the plasma physics inside of a fusion reactor. And we're even seeing this being applied with industrial HPC. Siemens Energy, in collaboration with AWS, built a AI model that accurately predicted the efficiency and breakdown of a steam-based generating plant, which Siemens produces. They're using this model to predict when they have to take down the steam generator, perform predictive maintenance on it, both ahead of a catastrophic failure, which of course is a big interruption and costs millions of dollars and actually produces a service interruption, but also to minimize the downtime, to decide when we actually need to do the predictive maintenance to keep the efficiency and the cost under control. One of the areas NVIDIA is investing in this is our Nvidia Modulus platform. So, these workflows, developing an AI that can accurately predict or based upon physics-based methods is an entire workflow. We're contributing to that with an open source project called Nvidia Modulus. It's providing kind of a high-level abstraction for domain experts. It offers scalable performance, so it can run actually on multiple GPUs across a cluster, and has some of the latest recently published model support in it. It has support for FNOs, AFNOs, PNOs. Basically, you use the actual physics equations as the reinforcement function for the neural net itself. So the neural net can learn multiple ways the partial differential equations want to be solved, and their operators as proxies, and of course run much faster. The third use case is the rise of HPC at the edge that we see. And here, there's a bunch of scientific experiments that are coming online right now. The APS, the Advanced Photonic Source, which has the ultra bright high energy X-ray beam generator at Argonne National Labs. Of course, the SKA Project Observatory, which is the world's largest radio telescope. The Diamond Oxford, which is the UK's national synchrotron light source. ETL, the Extremely Large Optical Telescope, which is the European Southern Observatory. LIGO, which I mentioned earlier, is the Gravitational Wave Interferometer, which is developed by Caltech and MIT. And DLR, which is the Stratospheric Observatory for Infrared Astronomy in partnership with NASA. Each of these instruments produces obviously a vast amount of data, and they want to collect that data. Of course, it's too large to store. It can't be operated as a batch, and often they're constantly running, looking for the needle in the haystack events that they're designed to discover, to understand, either in space or in science or in nature. AI and compute real-time stream processing is being employed to whittle that data down 100 or 1,000-fold, and then produce only the data that needs to actually be processed and connected directly with the data center or the supercomputer to inspect and learn. And often these workflows, as has been mentioned at this conference, have an active learning component. So as they're studying the data, they're refining their model, which is being pumped back into the edge device, which is looking to optimize and extract the data efficiently. This is really hard. Obviously, you're dealing with massive amounts of data, so minimizing copies and keeping the data flowing seamlessly throughout the system, throughout the network, and to the actual computing device is paramount. It has to scale, so as the experiment gets more complicated, often they want to scale dynamically and apply more resources to it, or leverage an existing supercomputer, which maybe have other use cases. Often we're combining multiple streams of data, so a lot of these instruments are multimodal. They have multiple different sensors that want to come together to solve a solution. But let's also not forget the developer. A lot of these scientific experiments are designed as experimental data, but not necessarily need to be programmed. The programming of the instrument and deploying and developing the AI models is as big as a part of the actual engineering of the physical instrument itself. So developers, users for these instruments need easy to use software platforms to code up in Python and apply modern AI programming techniques to become part of the instrument itself. Another example of this actually is in lithography, and it's using AI-based methods to go beyond the natural optics that are naturally allowed to. This is work being done at Argonne National Labs. They developed a neural network called TychoNN, which is actually an AI model. And what it does is it actually takes the raw diffraction data from the microscope itself. And that diffraction data itself is basically a highly blurry image, and actually tries to reconstruct what kind of diffraction what kind of material could have produced that diffraction pattern. So now we're looking beyond the actual wavelengths of light to look at the diffraction and the different interferences of light to reconstruct what would normally be seen in what we would expect from a typical microscope image. To do this, you can do this certainly offline, but it requires a fairly extensive sort of first principles calculation, not dissimilar perhaps from seismic imaging, but now done on a microscope scale at a batch level. But by deploying AI, they develop a neural network that actually minimizes the computation. Using a technique built from autoencoders, using AIs for compression, they actually can reduce the number of layers down to a smaller resolution to find what effectively is the eigenvector and the eigenmatrix of the problem, and expand it back out to reconstruct the image. This dramatically reduces the computation by about 300x, and is basically an approximation, a quite good one, of actually what is this microscope actually seeing, based on using an AI technique instead of first principle math and physics and applying computation, turning this into a real-time kind of instrument. And psychography is a very hot area right now, and is one of the really interesting applications of AI. This isn't just for silicon and semiconductor technology, but it also could be applied to biological methods. In fact, work being done at Lawrence Berkeley and Berkeley Labs is building a new kind of microscope, one which actually uses AI to reconstruct what biology can be doing as it's happening. So this is we'll show a video of this, and you can see this is actually a new light field camera that's being used to actually reconstruct biology as happening in real time. So please go ahead and roll the video.
Now with Clara Holoscan and Nvidia Index, we can visualize the entire large volume of living cells in real time as the data is being recorded directly from the microscope. Watching these living cancer cells move about, we can see normal healthy biology and malignant processes at the same time. The fluorescent marker rendered in blue marks nuclei, which we see splitting to form two cells from one cell. A hallmark of cancer is cell division occurring more frequently and with less error checking than normal healthy cells. Using Berkeley's lattice light sheet microscope, the ultimate high resolution allows scientists to see what is hidden to normal light optics, not seen using traditional microscopes. As we zoom in, watch cancer cells display what is thought to be a rare event, even for cancer cell lines. See one cell split into 3 cells. This phenomenon has only been reported anecdotally in a couple of scientific publications. Scientists do not yet know what we will see, but this technique, enabled with real-time processing and visualization, now allows the scientific community to discover new, unseen events like this. Let's see what the future has in store.
So this technology actually took the light sheet microscope and actually reconstructed that image far beyond what the traditional optics would do. This was a live image from the researcher. They can actually move around and explore the space as the biology was actually happening. Normally this would be done as basically an offline process. You would place something like this in an electron microscope, which of course would destroy the sample and the biology, and you'd only get a static image. Now, we're applying AI to tychography, we can actually reconstruct and build these kinds of cameras and actually witness biology at a resolution way finer than we could before. The researchers that did this used our Holoscan technology. This is an SDK that's available from Nvidia. Basically, it's a streaming reactive framework, so you can build your own pipeline for processing the raw data from a sensor, applying AIs, and then producing whatever output you need. In the case of them, it was an image. It's optimized for high performance, low latency, service-oriented, and multi-model. It's just minimized your copies, either working with our AGX platform, which is the embedded version of our GPUs, or can actually be deployed on actual servers or even clusters if necessary. So if you're interested in this work, please check out NVIDIA, the Holoscan SDK. The fourth workload I wanted to talk about was digital twin. And as this morning, I think Rev did a great job explaining that building digital twins, either at the molecular, the plant or factory level, the city level, or even the planetary level, makes supercomputers another instrument of science to be able to actually simulate all these things and understand them in a virtual world in ways you can't really in a physical world. And further, by applying modern scale-up simulations, as well as these new real-time AI-assisted simulations techniques, we can build these systems, these digital twins that actually are interactive in real-time environments. So another video I wanted to show, which is actually the atmospheric, this is the application of the ForecastNet technology being applied to a digital twin on Earth. So if you could roll this video, please.
Climate change is making storms both stronger and less predictable, leading to more fires, floods, mudslides, heat waves, and droughts. Atmospheric rivers are enormous rivers of water vapor in the sky, each carrying more water than the Amazon. They provide a key source of precipitation for the western U.S., but these large, powerful storms can also cause catastrophic flooding and massive snowfalls. Nvidia has created a physics ML model that emulates the dynamics of global weather patterns and predicts extreme weather events, like atmospheric rivers, with unprecedented speed and accuracy. Powered by the Fourier neural operator, this GPU-accelerated, AI-enabled digital twin, called ForecastNet, is trained on 10 terabytes of Earth system data. Using this data, together with Nvidia Modulus and Omniverse, we are able to forecast the precise path of catastrophic atmospheric rivers a full week in advance. ForecastNet takes only a fraction of a second on a single NVIDIA GPU. That's a staggering 5 orders of magnitude faster than traditional weather forecasting models. With such enormous speed, we can generate thousands of simulations to explore all possible outcomes, allowing us to quantify the risk of catastrophic flooding with greater confidence than was ever possible before, including rare but dangerous extremes that may be missed by traditional numerical simulations.
With a combination of AI plus the digital twin, the Earth becomes a digital experiment. And we can interact with this digital Earth by changing initial conditions, changing weather conditions, and changing, of course, describe a future Earth which may have different climate conditions and a different environment. Okay, the last use case, of course, is quantum computing. And I don't need to remind this community is a very hot topic in computing in general. However, mapping the Schrodinger equations to computer science algorithms is still in its infancy. And supercomputers have a very important role to play to actually simulate and emulate these future computing technologies. There are lots of players in this space, lots of different frameworks that are building quantum frameworks that can be used to emulate or give computer scientists the tools they can to figure out how these future computing platforms are going to be used. Our job, of course, is to basically provide some of the core mathematics. So we have a library called cuQuantum, which actually does state vector and tensor network primitives. Math primitives successfully is a math library that's been integrated in all these different quantum frameworks. And the results are pretty significant. So today, from Pascal, AWS, Xanadu, and Meniton, who's actually trying to develop a quantum algorithms to be applied for drug discovery, GPUs offer a huge performance benefit over traditional CPU-based algorithms. And again, these are all integrations using our cuQuantum library. I think supercomputers in general are the platform for the next wave of computer science, the one that's going to be powered by quantum computing in the next decades. Okay, so as a result, we're super excited about the supercomputers being built for the modern workloads of AI. And these are just some of them. Certainly the Perlmutter system at NERSC has just already been built and been used for some of the demos I just showed you here, and for the applied science, of 3.8 exaflops of AI performance. Nvidia is building EOS. This is our own supercomputer that we use for developing our products, as well as for our self-driving car and Nvidia research. That'll have 18 exaflops of AI performance built on our Hopper GPUs. CSCS, which will be built next year, will have 20 exaflops of AI using our Nvidia CPUs and GPUs. And the Chineka system, Leonardo, with 10 exaflops of AI, also leveraging our quantum. The new system, which is being announced here at ISC, is the Venado system, which is be hosted at the Los Alamos National Library, built with our partners from Hewlett-Packard. Venado will be the first US-based ARM system with Grace and our Grace Hopper superchips. It'll have 10 exaflops of AI performance, and actually quite a bit of memory bandwidth, over 7,700 terabytes of aggregate memory bandwidth in the system. The goals for the system is to do fundamental open science, material science, leveraging VASP for DFT calculations and developing some of those AI accelerated methods and potentials. For doing the lithography work I talked about prior. Also be used for energy research, particularly emulating and simulating power grids as a digital twin. And for fusion energy research. We're also super excited they're using this to actually develop unmanned vehicles, which are 5G accelerated drones effectively, that can help detect and fight fires. I mentioned fusion energy. Fusion energy is also an excellent candidate for building digital twins. So bringing together the Omniverse technology that was talked about this morning, native simulation, as well as AI-assisted simulation, digital twins are an important part of defining the future of fusion energy. So in one last video I wanted to show you, which is the work being done at ICF at the UK Atomic Energy to actually develop and design their next fusion reactor, both physically as they're building it and a digital twin in parallel. So with one last video, let's show what's going on there.
United Kingdom's Atomic Energy Authority and University of Manchester are partnering to produce carbon-free, clean power. They're testing Nvidia Omniverse to accelerate the design and development of a full-scale fusion reactor, a small star held inside a magnetic bottle. Building a digital twin that accurately represents all reactor components, the plasma, and the control and maintenance systems is a massive challenge, one that can benefit greatly from AI and exascale GPU computing. The design of the physical reactor itself involves numerous experts from a variety of domains. With so many moving parts, it's critical to keep scientific, engineering, and design experts and their data in sync at all times. With Omniverse, teams can connect disparate 3D design, engineering, and simulation tools so they can collaborate on a single source of truth. Simulation of the fusion plasma itself is also a grand challenge. Scientists developed Omniverse extensions to ingest data from 2 simulation software programs. The Monte Carlo Neutronics code GANT4 enables them to simulate neutron transport in the reactor core, which is what carries the energy out of the reactor. And the Jorek plasma simulation code simulates visible light emissions, giving insight into the plasma state. In the future, scientists will use Nvidia Modulus, an AI physics framework, to further accelerate their simulations. With a physically accurate digital twin of both the reactor and the internal reactions, researchers can work to create AI-based systems to help control and sustain the burning plasma. Maintenance will be performed by robots trained and re-optimized in simulation with large amounts of synthetic data generated in Omniverse. This helps them to perform tasks accurately before being deployed into the real world. In the future, the Omniverse digital twin will be synchronized to the physical reactor with real-time streams of sensor data. Researchers will be able to explore hypotheses by first testing in the digital twin before deploying changes to the physical reactor, boosting performance, improving predictive maintenance, and reducing downtime.
Super cool. And also a great example of how supercomputers are going to be used moving forward. So that's the software. And we see both simulation, HPC plus AI, HPC edge, digital twin, and of course quantum computing being an important part of the modern supercomputer. And Nvidia is investing in all those areas with their different SDKs, so please do check them out. Of course, that's the software. It wouldn't be an Nvidia presentation without providing some insight on the hardware as well of what's going into these modern supercomputers and what people are using today. Recently, we announced our Hopper GPU. This is the GPU that's going to be deployed moving forward. This is one of our most advanced chips ever. It's 80 billion transistors. It is specifically designed both for HPC and AI. It's supporting all the mixed precisions from FP64 all the way down to FP8 to do both the simulation and the AI workloads. Most interestingly, transformer-based models. Transformers, which are the majority of AI that's being done today. I think 70% of the AI papers published today is based on transformers. And we specifically designed this GPU with a custom transformer engine to apply models like GPT-3 developed by OpenAI for conversational large language models to be deployed and trained for science use cases with this GPU. It has our 4th generation NVLink for connecting them all together, supports confidential computing and multi-instance GPU, as well as new instructions specifically for dynamic programming. Our DPX instructions were designed in collaboration with the genomic sequencing community of how can we advance or improve the instruction set of our GPUs for better use case for genomic sequencing, optimization planning, and anywhere you can apply dynamic programming techniques. Its performance compared to our previous GPU is obviously a step up from anywhere from 2x to 3x, and in some cases, for the genomics Smith-Waterman applications, a 7x improvement prior to the prior A100 GPU. But we didn't stop there. We've been working on building GPUs for 15 years now for HPC, and the world has largely adopted accelerated computing as a path forward for optimizing computation. That work has been done, obviously focused on the most important applications in HPC, the top 50 apps, which typically represent maybe 60% of the workload in an open science supercomputer. But what about the long tail, the rest of the 40% of the remaining applications, which are legacy applications, perhaps written in Fortran, which was, of course, developed in 1957. It's estimated there's over 1 billion lines of Fortran in HPC today, and not all of it's going to be necessarily accelerated, nor can it be. The workload may be too spread out, or the application may be certified, and it's difficult to move and be recoded and move to an accelerated platform. For that use case, we developed our new CPU called Grace. This is our Grace Hopper module. On the left-hand side is our new Grace CPU. This is an ARM-based, leveraging a standard ARM architecture of V-class core, and combined directly with our Hopper GPU on the right. And you can see it's designed to have the densest possible NVIDIA accelerated solution. It actually supports a 900 gigabyte a second interconnect between those two super chips, basically radically limited dies, to provide the chip-to-chip coherence. In addition, that coherence link can also be used to connect two Graces together to build a Grace superchip. This is a 144-core CPU. It has 1 terabyte of memory, as you can see along the side, and since everything's soldered down, put close to it, it's a 1 terabyte a second of memory bandwidth. We're also leveraging the LPDDR technology, which is designed for embedded SoCs, but applying it to data center. We worked with one of our memory vendors to build an ECC and data center ready memory technology. As a result, this processor actually has double 2x the perf per watt for CPU workloads. And there's a lot of interest in deploying the Grace superchip for legacy CPU workloads, especially in this era where energy efficiency is paramount. Some of the performance, obviously, by bringing the GPU and CPU closer together, we're seeing 2 to 5x-ish performance improvement in HPC application performance. And even with traditional applications like Wharf or OpenFOAM, where we have a large library of CPU applications, they can take advantage of Grace's improved performance, its SVE, and of course, its energy efficiency. We don't stop there with just the chips. Of course, we want to connect and build entire supercomputers and data centers. And our investment here is basically bringing some of the ideas that were first formulated in the cloud to supercomputing itself. To build native NVIDIA cloud-native supercomputing, where we have in-network computing, we have zero-trust models with multi-tenancy, doing computational storage and enhanced telemetry, all based upon our networking products, ranging from the Quantum 2 InfiniBand switch to ConnectX-7 to Bluefield SmartNICs to the Skyway Gateway, and of course the software using for managing all that, the UFM. One of the exciting parts of cloud-native supercomputing is the idea of performance isolation. Instead of where your use of your supercomputer does not affect the usage of others and vice versa. Which is obviously very important to the cloud, where multi-tenancy is paramount. We can bring that technology to supercomputing. This is a chart for lamps, and basically a histogram of the response times for the compare and exchange operations that are happening inside of lamps. As you can see, if you're a single tenant, you're getting great throughput. But as you have multiple users on the system, your performance can degrade, and the performance of your collective operations can smear out, and you're affected by others. By applying cloud-native techniques and performance isolation, we can actually build a software-defined network that ensures a certain amount of performance and gives you, even in a multi-tenant situation, predictable performance and peak performance, and keeps other users out of your way of your calculation. This platform, it has both support for doing different levels of security, networking, isolation, and also is integrated with some of our storage providers. We call this platform DOCA, and I also encourage you to check it out as well. We have multiple engagements going on with research clusters to help develop and work and partner as we develop it. At Cambridge University, our own superpods, but also at Durham University and the Thor system of the HPC Advisory Council. Here at ISC, we announced 2 more collaborations on DOCA. The Lone Star system at TAC, which is looking at SmartNICs using our Bluefield technology, basically ARM cores at the NIC level. And then also at Los Alamos National Laboratory, where we have a goal of providing a 30x performance speed up by doing in-network computing. Some of the calculations that we do in HPC actually make sense to be performed in the network. By doing so, we can reduce the network traffic altogether by performing those operations in the network, and we're collaborating with Los Alamos to explore that space, both how to program and actually how to take advantage of in-network computing as a primitive for HPC. And the last announcement that is being made today was that Nvidia has now partnered with Cyprel to help advance the ARM ecosystem here in Europe and around the world. We're very excited to be doing the things that ARM enables the HPC ecosystem to do, to build new, interesting, more power efficient, more creative architectures, system architectures, for optimizing HPC, for optimizing AI, for getting better energy efficiency, and customizing our solutions for what HPC and our supercomputing world needs. Our partnership will start with integrating our platform and sharing it with Cyprel, also by building dev platforms, by helping the community take advantage of ARM technologies like SVE, and exploring as proxies future ARM integrated GPU solutions for better programmability and, of course, increased performance. And that's it. Accelerating a new wave of innovation of scientific discovery consists of the 5 things that our new modern supercomputers are going to be asked to do. Ever increasing and larger scale simulation, that will always exist and continue to exist in order to solve the grand challenges. But increasingly, building modern supercomputers involve making them great for HPC plus AI workloads, for integrating them as part of science as the instrument itself, as I showed you today. Also being a digital twin to some of these large experiments like developing the next generation fusion reactors. And of course, being the development platform, the dev kit, if you will, for the future of quantum computing. Those systems are coming together and being built now, and NVIDIA is building not just that, helping with the software and open sourcing and providing contributions in the software for this ecosystem, but also, of course, providing the hardware components, which we believe are a great fit for these 5 workloads. And of course, going beyond, we're a big partner with the cloud and the hyperscalers and what they are doing, and bringing some of that technology and bringing cloud-native supercomputing to supercomputing itself. With that, I want to thank you for listening to me today. I'm going to end with one more fun video, which I think you'll enjoy. So thank you very much.
Ready, go!
Once upon a time, it was all fun and games. Nvidia started off by making chips for video game machines. Graphics became serious business when people started using Nvidia for blockbuster movies, medical imaging devices, and the world's most powerful supercomputers. And then one day, researchers discovered that our technology was perfect for AI. Today, Nvidia is the engine of AI. Engineering the most advanced chips and systems, and the software that makes them sing. So robots can lend us a hand. Cars can drive themselves. And even the Earth can have a digital twin. We live to tackle the world's biggest challenges. And don't worry, we still love our fun and games.